Hello, everyone. Thank you for joining in today. Uh, I have with us Raghunath sir from Cheenta Math Olympiad teachers team, and we are planning to discuss the problems from Indian National Math Olympiad 2023. This is the problem one for today. So, Raghunath, could you explain the problem?
Yes, so first let me paste the problem.
Yeah,
So
sure.
here comes the problem.
All right. Yeah, it's visible.
Yeah, so we have a finite set of positive integers.
Okay.
So let's say we have a set,
Uh huh.
yes, and a few positive integers, say x1, x2, x3, and so on.
Okay.
So there are 23 ordered pairs in S crosses, right? So such that it is a perfect square. So for
Okay.
example, if you take two numbers
Uh huh.
x2 and x3, then we count this as a ordered pair whose product is a perfect square if x2 times x3 is a perfect square.
Okay.
So prove that one can find at least
So when you say ordered pair, x3 comma x2 will be a different ordered pair, right?
exactly, yeah. X3 comma x2 is considered different from x2 comma x3, but if the product of x2 and x3 is perfect square already, so x3 into x2 will also be perfect square.
Perfect square, right? Okay. Go
so
ahead. Yeah.
so that's one property that we can assume from the question. So prove that one can find at least four distinct elements in S so that none of their pairwise product is a perfect square. So for example, uh, if you have some um, let's say 1 4 7, maybe not 4, we can take 8 and 11. So this is a set of four numbers whose pairwise product is not a perfect square. So
Okay.
that means none of their pairwise product is a perfect square, which means like 1 into 11, 1 into 8, and then 8 into 7, and
Uh,
like that.
okay.
So that's how so they are telling us to find such four numbers. I mean, we can always find such four numbers. That's what they are asking us to prove.
Okay. Okay.
So
Given that
now,
there are 2023 ordered pairs.
yeah, given that there are 23 ordered pairs, so this is one of the property of the set S.
Got it.
So with this property, we shall try to prove that. So first, let us see something that when will the product of two numbers become a perfect square? See, for example, we can assume that a number without loss of generality,
Uh huh.
we can assume any number is a product of powers of primes, right? By the fundamental theorem of arithmetic. So we
Right.
say p1 power alpha 1, p2 power alpha 2 till pk power alpha k. Let's say this is now some number n. So
Okay.
I'm going to you know just split all these, any number into primes and a perfect square. So how can this be done? So we can take, say, an example: p1 power 3, p2 power 4, and p3 power 5.
Okay.
So we write this in the form p1 into p3 times p1 square, p2 power 4, p3 power 4. So why did I do this? Because all the exponents of this primes are now even, which means I can make it a perfect square by
Right.
p1, p2, p3, the whole square,
Right.
where the exponent of these primes are 1, right? We tell these primes,
Or
so we
this
call
product.
them,
You do mean this product?
Yeah. I mean, the set of those primes. I
Okay,
mean, exactly the set formed by these primes P1 comma P3.
okay,
I call them as the standalone primes
okay,
of the number.
okay.
So, so what we have to realize here is for each given number, we have a unique set of standalone primes. We
Right.
can do that in a unique way because since given that the powers of these primes are 1, right? So you just factor out that 1 prime if alpha I is odd,
I see.
and you don't do that if alpha I is even.
I see.
So for each number n, the set thus formed is unique.
Uh-huh.
Okay. Now let's come to
So
two
just to make
numbers.
this clear,
Yeah.
the number can be entirely composed of standalone primes. For example, 15 is 3 times
Exactly.
5. So both 3 and
Exactly.
5 will be standalone primes.
Exactly. In that case, 3 and 5 both are called both are the set of 3 and 5 is the standalone primes for 15.
Got it. Got it. Okay.
That's correct. And now let's consider two numbers n1 that has, let's say, p1 into p2 into
Okay.
till some pq
Okay.
times let's say x square, where this is written in the form that I have told,
Uh-huh.
the product of standalone primes times the perfect square,
Got it.
and we know this is a unique form. And n2 is let's use r1 into r2 till rs
Okay.
times some other perfect square y square. So when will this become first let's see how this multiplication look like. N1 times n2,
Uh-huh.
it will be p1 into p2 times pq
Uh-huh.
into r1 times rs
Uh-huh.
into xy the whole square.
Right.
Suppose we want n1 into n2 to be a perfect square.
Right.
Let's say some z square.
Right.
So let's worry about these primes.
Okay.
What should they be and how should they behave? So first, since z square is a multiple of xy the whole square,
Right.
then can I say xy the whole square divides z square
Yeah, of course.
because it's a multiple.
Right.
This implies xy divides z square. Sorry, xy divides z, right?
Right. Right. Perfect.
So hence I will write z by xy as some t.
Okay.
Then what do we get? P1 into P2 till PQ, where all P1 to PQ are distinct primes,
Okay.
times R1 into R2 till RS, where R1 to RS are distinct, equals T square.
Got it.
So when will product of distinct primes, I mean you have some distinct primes here and you have some distinct primes here,
Right.
when will that be a perfect square? So for example, we know that P1 divides T square, right, from this
Right.
equation.
Right.
This implies P1 divides T. I mean,
That is
not only P1, let's say Pi divides T.
right.
So that implies Pi square divides T square, right?
Right.
When we square it. So so let's say P1 is here. So there should be a prime P1 that is hidden here, right?
That is correct. In
Only
fact,
then I can factor out two Pi
two
square.
pieces of P1. Correct.
Yeah. So similarly, all of these primes are present here.
Correct.
Similarly. So obviously now we see that S is greater than or equal to Q. The number of primes here must be lesser than the number of primes here. Only then you can put in all the primes in the R's.
But the same logic will follow from the right hand side. I mean,
Exactly. So
Q
if
will
I
also be greater than S.
exactly. So similarly,
Yeah.
we get Q is greater than or equal to S because we have to fit in all the R's. I mean, one more copy of R must be present in piece. So we have Q is greater than or equal to S, and both imply that Q is equal to S.
Right.
Now, if Q is equal to S and each of the P's is equal to some R's,
Right.
so then each of them, I mean, both of them must be equal, right?
Correct. Absolutely.
Because to be rigorous, maybe you can assume that without loss of generality, Pi to Pq are in increasing order and R1 to Rs are in increasing order. Then P1 equal to R1, P2 equal to R2, and PQ
Yes,
equal to RQ.
that is
So
correct.
hence, what do we conclude here? N1 times N2
Right.
is a perfect square.
Right.
If and only if the set of standalone primes of N1 and N2 are the same.
Exactly the same. Yeah.
Are exactly the same.
Correct.
So now this is what we have observed, right?
Yes.
So how this will be helpful for the question. So remember that we need 2023 ordered pairs of x comma y such that xy is a perfect square. So
Right.
how should I get such a square? I mean such a set. So first let's see how these properties fit in. Suppose if you have x1 and let's say the without I mean let's say the standalone primes are p1 to pq of
Okay.
x1. If there is one more number that multiplies with x1 to form a perfect square, then
Uh-huh.
obviously that should also have the same standalone prime set.
Right. That we just proved.
Exactly. And similarly, if x3 forms perfect square with x1, so that should
Right.
also be standalone primes. So
Correct.
let's say that S1 is the set of numbers which multiply with x1 to form a perfect square. Now, what do we see here is if xi and xj belong to S1
Right.
for any ij, if xi and xj belong to S1, then
Then they
both
have
of
the
their
same.
standalone primes.
Absolutely.
Exactly. So their product should also be a perfect square.
Right.
So do you see the difference that we have defined x3 as a number which when multiplied with x1 forms a perfect square, but what we are ultimately ending up is if you take any pair of numbers, it will be the product will be a perfect square. So we can
Right.
see that all the I mean let's say
Because
there are
okay, okay. So I see what you're saying. So you're saying that if x2 and x3 are two numbers such that x2 times x1 is a perfect square and x3 times x1 is a perfect square, then x3 times x2 will be perfect square.
exactly, that's where we have landed up here
Right.
from this standalone primes observation that if it satisfies for one number and you group
Right.
together all such numbers, then if you take any pair out of the group,
Correct.
then it will have the same standalone primes, and hence the multiplication will be a perfect square.
Got
So
it. Yeah.
with this, say there are n1. Say there are n1 numbers in this set.
Okay.
Then how many ordered pairs do we get? Oh, n1 is used. Maybe let's use some other number, say m1.
Okay.
How many ordered pairs do I get? So ordered pair means two numbers. The
Right.
first blank has m1 choices,
Right.
and the second blank has m1 choices. So there are in m1 square ways that I can pair up the two.
Because
numbers.
x1 comma x1 will also be
Exactly.
Sort of a pair.
Exactly. So that will also be a pair, right? So if the two are equal, obviously it will when multiplied it will form a perfect square. And
Perfect.
if those two are not equal, then we know that for any xi and xj, you have the same standalone primes for those two. So
Right.
that is okay. Now let's go to, so we have like picked up all the numbers that when multiplied with x1 is becoming x square. So let's say some x10 does not belong to this set S1.
Okay.
That means what? X1 into x10 is not a perfect square. So that behavior, that x1 times x10 is not a perfect square, is carried to each and every number of S1. The same behavior is carried because this is an if and only if statement. So if n1 into n2 is not a perfect square, then n1 and n2 are having different set of standalone primes.
Correct.
Which means 10 is having a different set of standalone primes from this.
Right.
Which means x3 and x10 are also having a different set of standalone primes, and hence it will also not be a perfect square.
Right.
So hence,
right.
whichever number is out of this S1, I do not consider that in in forming a perfect square when multiplied with any of these numbers inside this.
Correct. I
So
understand.
this essentially what does to the set, this property makes a partition of the set.
Okay.
Say S3, some S4, something like that, S5. So, what do I mean by S2? I mean that I group together all the numbers in the set S that when multiplied with x10 forms a perfect square.
Got it. Yeah.
Something like that.
Yeah.
So we can just keep on inductively defining this until all the elements in the sets are exhausted.
Correct.
And I know how many ordered pairs are there in each set.
Each set produces mi square.
Exactly.
Of ordered pairs. Correct.
So what I want essentially is summation mi square be equal to 2023.
Correct.
So this was the question that they are essentially trying to ask us in this way, where I goes from 1 to number of.
If we can show that we need at least 4 perfect squares,
Exactly.
then we would be done.
Exactly. If you could show that there are 4 such partition, then what you do? Then take one number from each
partition and you can do this. Okay.
We know that one number from each partition cannot mingle, so
Correct.
they cannot do this, right?
Right.
So
right. Very nice.
That's what. And also, this is if and only if you have less than 4 partitions, then you cannot take, because by pigeonhole principle you will get some 2 in one partition,
right?
And that will form a perfect square. So what we have to prove is that the number of partitions must be greater than 3. Correct. Because if it can be more than 4, 4, 5, 6, also that's fine.
Right.
But more than 3 is what we are trying to prove.
Right.
Where here small n stands for number of partitions of S.
Right.
So let's see. what is so unique about this year? Yeah,
So basically, we have to show that if we want to write 2023 as a sum of perfect squares, then we have to use at least four perfect squares.
exactly. We need at least four such perfect squares. So, suppose m1 square is 2023. Obviously, no square can end with 3, right? It seems odd.
Okay, yeah, 2023 is not a perfect square, correct?
Perfect square. So, m1 square plus m2 square is 2023.
Okay,
So, here maybe we can use some modular arithmetic,
yeah,
because there are many cases we can't try manually. So, maybe we can eliminate some cases. For example, let's go mod 8. What is
okay,
the remainder when 2023 is divided by 8? It is 7, right?
okay,
7 mod 8.
yeah.
So, but let's also see what are all the, um, I mean, the
So,
residues
right,
that 8 leave when a square is divided by 8.
correct, correct.
So, we know that 1 square leaves a remainder 1, 2 square 4,
Uh-huh.
3 square 1,
So 1,
4
4, and
square.
0.
Exactly, 1, 4, and 0. You will just get the same thing again.
Right,
So, the only possible reminders are 0, 1, and 4.
correct.
So, can you put in two reminders from
Uh-huh.
from the set 0, 1, 4 to
Uh-huh.
add up to 7?
Now you can't.
We can't, right? Because now the cases are reduced very much.
Yeah.
So you can just try all cases. I mean, maximum you can reach. I mean, you can't do 7, right?
Yeah.
Now let us do for 3.
Yeah.
This will be. Is it possible to reach 7?
No, it's not.
No.
Then you can
No.
at most you can reach
4,
6. Yeah.
4, 1, and 1.
Yeah.
And if you go above 8,
Yeah.
then you
That's
will you even then you can't reach 7. The maximum thing above 8 is what? 4.
5. Yeah. 4. Yeah. 4.
So that is also not possible, and below 8 also direct sum of 7 is not possible. Just
Correct.
some few case works. So you can easily eliminate this also.
Correct.
Then we can easily prove that it must be the number of partitions automatically be greater than or equal to 4.
Greater than 3. Absolutely.
Yeah,
So you can choose 4 pieces from the 4 partitions and they will not mingle as you mentioned,
exactly.
and you will be done. Okay.
Exactly. And there do exist such a thing for 4. I
Ah,
think it is 9 squared plus 9 squared plus 30 squared
uh-huh.
plus 31 squared.
Oh, really? Okay.
See, this adds up to 2023. So
Okay.
it is possible to build such a set in which only 4 partitions are there, and you
Uh-huh.
just pick one from each so that their multiplication will not be a perfect square.
Great. I think this is a very nice problem.
Exactly. It uses, I mean, in set theory, we also do equivalence classes, right?
Correct.
So this deals about the equivalence relation. So that two numbers in a set, two numbers multiplying to form a, I mean, um, you put this symbol, I mean, x1 is equivalent to x2
Right.
if they multiply to form a perfect square.
Correct. Correct.
And you don't put that relation if they multiply to not form a perfect square. So that forms a equivalence relation
Right.
kind of thing. And they form all equivalence relation. We know they form the equivalence classes form partition of a set.
This is fantastic. Thank you, Raghunath,
Yeah.
for this wonderful discussion.
Yeah.
I hope to come back again with another problem with Raghunath sir. Just let us know in the comments section if you like this new format of our discussions in our YouTube channel. And if you like Cheenta's work, if you want to do outstanding mathematics or physics or computer science, you can visit cheenta.com for our courses. Until then, next time, stay well and keep on doing great mathematics. Bye.